is the mechanism of this motion. One thing to notice is that the direction of propulsion depends on the polarity. In the movies that I showed you so far, it was that this hedgehog, the nose of the sphere, leads the way, and the sphere just follows. If you do the experiment with particles that prefer perpendicular, that prefer tangential alignment at their surfaces like these particles, then even by symmetry you would realize that left and right are the same thing. So there should be no reason for the particle to understand which way to move. And indeed, when you apply electric field to such a configuration, you would see no motion. So the thing here is that in order to swim, the swimmer should have some asymmetry. And I was really stunned to see this painting in the Museum of Modern Art in New York City. The artist showed the perfectly symmetric flow around this blind swimmer. This is the name of the title of the painting. But then in the core you see asymmetry of the thing, so that the blind swimmer can choose the direction in which to swim. You know that you're not allowed to take pictures, so this is why I put myself in the picture, so that I wasn't guilty of the crime somebody else was. So one thing to think about it is that okay, if you have this asymmetric thing, maybe when you apply the electric field, because the Lie crystal director likes to realign in response to the electric field, maybe that is the reason for motion. And we did the experiment with these droplets and with these particles. It's two of them. And yeah, they are kind of moving, but they are kind of very tired of doing so. They move very slowly, and it turns out that this is not the mechanism. And we verified that by using a Lie crystal with zero dielectric anisotropy. So in that case, the director field doesn't change when you apply the electric field, but the propulsion is still there. So let us come back to the main idea of electrophoresis. To have electrophoresis, you should separate the charges in space. If they're close to each other, the electric field acts on them. It's like a neutral, electrically neutral system. There is no force in either direction. And in the case of isotropic electrolytes, the separation of charges occurs because of the properties of the particles. They have these polar groups that dissociate in water, and that is how you separate the charges. But I will argue in the next subsection that in the liquid crystal you don't need the interfaces to separate the charges. All you need is that the medium itself, even without particles, would separate charges in absence of the electric field. And the reason is because the director is distorted and because the liquid crystal is anisotropic. So let's explain what I mean by this concept. So imagine I have a sphere with a symmetric director field. It's a normal orientation. It's like a Saturn ring or two defects at the poles. And there are always some ions in the bulk of any fluid, including a liquid crystal. And the system is electrically neutral. But I apply electric field now, and the electric field causes the ions to move around. The positive ions would move to the right, and if they are in the proximity of the spheres, because it's easier for them to move along the director, as we saw for the colloidal particles and their Brownian motion, the motion parallel to the director is always easier than in the perpendicular direction, I would realize that they will assemble at the left surface of the sphere. Negative ions would move to the left. If they are here, they would just go to minus infinity. But if they are here, the rail of the director will force them to concentrate on the right-hand side of the sphere. So if I wait for some time for these charges to move, then I would realize that they should create two clouds, a positive on the left-hand side and the negative on the right-hand side. But since I now separated the charges, there would be a Coulomb force that is the product of the charges by the electric field, that would try to move these clouds to the left and to the right, and since this is a barrier for the ions to move, they would move around the sphere. And so I would guess that the electric field that caused this separation would produce charge that is proportional to the electric field, and the force that moves the clouds of now separated charges would be another degree of the electric field. It's the product of the charge and the electric field. Since charge by itself is proportional to the field, this force is proportional to the square of the electric field. And let me see, I moved there. Now let's see what would happen if I change the polarity of the field. So I don't know why it's not working. If I change the polarity to the opposite, then of course the clouds would change their position. The negative charge will now be on the left, the positive on the right. But what matters is the product of the two. So if I take the product, then it turns out that these flow directions are exactly the same. So the flows, the directionality of flows does not depend on the polarity of the field. And this is an important thing, but it would depend on the director gradients. If, for example, now instead of this perpendicular anchoring, I am using a sphere that sets tangential anchoring, then when the field is applied, I would again have the separation of charges, which is now opposite to what is on the top. Since the field is in the same direction, my flow directions will be opposite. So the flows that I induce by applying the electric field to the deformed nematic are not dependent on the polarity of the field, but they are dependent on the gradients of the field, how the director is arranged. And then you do the experiment. You produce two cells, one with particles that have normal anchoring, and you place it in the shallow cell so that this hedgehog kind of spreads into the equatorial ring. And you do a similar experiment with a particle that sets tangential anchoring. And you measure the velocity by putting some tracer particles, fluorescent particles, in the Lie crystal. And you just observe the velocities of these particles, and you map those velocities as the function of coordinate. And you see that when you apply an AC electric field, there is a stream of flows. In this case, the flows are away from the particles along this equatorial direction and towards the particle in the vertical direction. Here it's totally opposite. In the vertical direction I have outgoing flows. In the horizontal direction I have influx. So what I said is confirmed by these simple experiments that depending on the director gradients, the directionality of flows might be different. And then you just combine these two pictures by kind of mentally taking one piece, one half of this picture and the other half of this picture, and you construct the dipolar structure of the hedgehog. So on the left and on the right you have different director fields. And then if you apply electric field to the colloid that is glued, you realize that there is a lost symmetry of the flows. The fluid now moves predominantly from right to left, and this is for the particle that is glued to the substrate. It's working like a pump. You just apply electric field, there is no gradients of pressure, but the fluid is pumped through the system from right to left, and you can even calculate how much fluid would pass through the different cross-section of this simple electric pump as the function of distance from the sphere. And so the glued particle causes electroosmotic flows in one direction around it. If the particle is free to move, then you would obtain what you already saw. The motion, electrophoretic motion of the particle either to the right or to the left, depending on the symmetry of the thing. And now you can develop a simple theory of what's going on by assuming that the director distortions are weak, very small deviations from the uniform background. And the point here is again in anisotropy of electric conductivity, that the ions prefer to move parallel to the director. When you apply electric field along the x direction, this anisotropy creates the separation of charges and flows in the perpendicular direction, and there is a component of the electric field that is induced in the system that is along the perpendicular y direction. And this perpendicular field leads to the density of charges rho as the function of delta sigma. This is the anisotropy of conductivity equal sigma parallel minus sigma perpendicular. And the gradients, how phi, the angle of director deviations from the horizontal line, changes along this vertical coordinate. And then by balancing the Coulomb force, the product of the charge and the electric field and the viscous resistance, you arrive at the conclusion that your velocity should be proportional to the square of the field and to the anisotropy of conductivity that caused this charge separation. And it's also proportional to the size of the particle. And a nice thing about it is that this velocity grows with the size of the particle. And the next experiment just shows that this expression is valid. This is how velocities change with the size of the particle. And this is how the velocity changes around a particle of a constant size when you change the electric field. So it grows as the square of the electric field. So it is kind of interesting to compare how fast are the flows caused by the liquid crystal electrolyte as compared to the flows in the Smoluchowski type of isotropic electrolyte. So the ratio of the two is expressed here. So you have the ratio of the epsilons, dielectric conductivity of the liquid crystal and water. Water is larger. And then you have the ratio of viscosities, obviously. But then you have a very important scale ratio. R is the relatively large size of the particle, which might be, let's say, 5 micrometers. Lambda D is the separation of charges in isotropic electrolytes. It's the so-called Debye screening length. And if you're familiar with it, you would know that in water, for example, it's just few nanometers. And this is much, much smaller than the 5 micrometers we have in the case of a liquid crystal. So as a result, these velocities are a few orders of magnitude in the liquid crystal are higher than in regular electrolyte. Another thing is that the velocity is proportional to E squared. The directions of the electric field and motion are not related. In linear electrophoresis, if I apply the field horizontally, the particle can move only along the horizontal direction, either parallel or anti-parallel to the field. In a liquid crystal, I can design an experiment in which the electric field is vertical, perpendicular to the field of view here, and the particles move in the plane that is perpendicular to that field, because all that matters for the directionality is the asymmetry in the plane of the observation, and this asymmetry is set by the director distortions. Of course, then you can design different schemes for the director. You can pattern it in such a way that it's circular, for example, and then you have two-dimensional control over the trajectories of the particle. In this case, they would follow the racetrack going in a circular direction. Or you can apply the electric field perpendicularly and horizontally. And here again, you would have possibilities to control the directionality of motion. One direction will be the normal electrophoretic motion that is proportional to the field in a linear fashion, and perpendicular direction will be proportional to the square of the electric field. And finally, you can even control the z position of the particles. Here I show that the particle that is active in the plane can be also shifted along the vertical direction. It's simply by applying a DC electric field that acts exclusively as a normal isotropic electrolyte and pulls the particle down or raises it to the top. So the next slide just shows you side-by-side comparison of normal classic electrophoresis in isotropic fluids and what the liquid crystal brings. In the linear case, only a direct current field can move the particle. If you change it to the AC field, then the particle will just oscillate back and forth. There will be no average displacement. Because of that, when you apply the electric field of a DC type, then the ions in the system would eventually block the electrodes and the electric field will go to zero. And in order to continue your experiments, you would need to stop, remove the field, and wait till the ions redistribute themselves. And so another thing is that only charged particles can be moved, and the direction of propulsion is limited by the direction of the field. And in the liquid crystal, it's a much broader range of possibilities. First of all, you can use an AC field, and that immediately eliminates the electrode blocking. You can create steady flows as long as you are applying the electric field. There is no depletion in the applied voltage, and the steady flows are very natural. The particles do not need to be charged in any way. No separation of charges because of polar groups at the surface, and the direction of motion is not limited by the direction of the field. So the only thing that is kind of not satisfactory at this point is that I can move those particles, and as I said, these particles that are totally symmetric, not totally, but quadrupolar type of a symmetry, these particles cannot be moved. But what if I need, for whatever reason, for separation or some delivery purposes, I want to move particles that set tangential alignment. And in the next section, I will show you how to do it, how to move these particles as well. And the main idea here is that instead of waiting for the particle to create the distortions of the director needed for this electrophoresis to work, you just pre-pattern the director field in the cell, and then you put the particles that can be of any of those types. So this surface patterning is achieved with photosensitive molecules. So here I show you the dye, azo dye, brilliant yellow, that has these two azobenzene groups. So when you irradiate a film of such a dye with polarized light, what happens is that these azo groups, they go into continuous trans to cis and cis to trans conformational changes, and they do so till the long axis of the molecules is realigned perpendicularly to the polarization of light. Because when it happens, the coupling between the molecule and the perpendicular electric field is no more efficient, and there is no trans to cis conformational change. And in that way, you align the dye molecules. And then you cover this aligned film of a dye with some protective layer of a polymer, and you have an aligning substrate that the director would follow, and typically it follows the orientation of this surface agent, this dye. So my colleague at the Advanced Materials and Liquid Crystal Institute, Chiho Wei, came up with a very nice idea to how pattern this surface alignment so that it would change from point to point. So what he does, he makes a mask, which is a thin metallic film with nanoslits, openings. These openings are of sub-wavelength scale. When light comes through, then because of some plasmonic excitations, the light that is polarized perpendicularly to these slits will go through. The light that is polarized parallel to the slits is not going to be transmitted. So you irradiate this film, this mask, with unpolarized light, and the outgoing light is linearly polarized. And now if you create a mask in which these nanoslits form a geometrical pattern that changes from point to point, the light that goes through would acquire linear polarization locally, and globally it will be shaped by the geometry of this mask. And then you irradiate the photosensitive substrate, the molecules will be aligned perpendicularly to the local polarization of light, and so two perpendicular transformations result in the pattern of molecular orientation that is the same as the pattern of these nanoslits in the photomask. And if you create this cell with two photosensitive substrates and irradiate both of them at the same time, you would obtain this pattern that is identical at the bottom and top. You fill this cell with the liquid crystal, and the liquid crystal will obey the surfaces, and it will establish itself in a variety of patterns, whatever you designed. It can be this circular configuration, it can be some stripes, it can be the two defects shown here, or it can be an array of defects shown on the right hand side. So now let's see what would happen to electrokinetics if I have a director field of this type in absence of any colloids. So as always, there are some ions, I apply the electric field, the conductivity is anisotropic, and I am continuing this thought experiment. The positive ions want to move to the right, but since they are in an anisotropic environment and the director is like a rail that tells the train which way to move, the ions move not only to the right, but also they are slightly shifted along the vertical direction. And the negative charge goes to the left, but also along the perpendicular direction, being guided by the director field. And so if I think a little bit longer, I would realize that this pattern separates the charges into lanes, and I do not need any interfaces for this to happen. And of course, since the electric field is still there, there will be a force that drags the ions to the right and to the left. And if I now have a liquid crystal placed in such a cell, and I add fluorescent particles, this chunk, then I clearly see that this simple pattern creates the electroosmotic flows. The flow here is of 5 Hertz. That means it's AC electric field, and it's easy to understand. It's exactly the same thing as before, that the change in the polarity of the field doesn't change the direction of the flows. It changes the locations of the ions, but since the force is proportional to the product of charge and the electric field, the net result is that the forces and flows are in the same direction. I can repeat the same consideration as before and end up with this formula that you've already seen, and then I can play with different patterns. For example, this is the pattern with 2 defects, and this is small water droplets. It's very hard to force a water droplet to move in a simple scenario, but here we can force the pneumatic to act as the pump by applying electric field, and this particle not just moves anywhere, it just moves and accumulates water at the center of this defect that was pre-patterned. This is the distribution of charges, and this is the experimental flows that such a pattern creates. You can also move other things like air bubble here, and otherwise it wouldn't be moved if it not for the electroosmotic flow in this pattern. And as expected, the larger the inclusion, the higher is the velocity of the larger is this the period of the structure, the higher is the velocity of motion. I can use the complex array of defects to create microvortices, and these microvortices are shown here, and this is of importance for technology. You know, at small scales, we are dealing most of the time with the so-called low Reynolds number regimes, and that means that all the flows are kind of laminar flows. If I want to mix 2 fluids, I have to wait a long time because it's only the mutual diffusion that would mix them. And if I have these microvortices, the mixing becomes much faster and much easier, just because the system mix itself thanks to the electroosmosis. So I just presented a very kind of the tip of an iceberg here. The theory of with the complete account for distribution of charges and the director field in assumption that the director field is not perturbed by the electric field has been developed by our colleagues Karma Calderer, Dmitry Golovati, and the rest of the group. So with this system you can also design opposite tasks. For example, if you do not want to mix things, you want, for example, to separate things. Imagine that you have some biological tests and you have colloidal particles that are surface functionalized to absorb different biomolecules. For example, you have particles that have molecules that would like to see the director around them perpendicularly aligned, or you have kind of particles that would like to see the director parallel to them. This might be an indicator of some biochemical reaction at the surface, but how do you know which particles are what? How do you separate these bold and the hairy particles? It turns out that you can do it. The net result is shown here. This is the hairy particles, they move to the right, and these are bold particles that are separated, they move to the left. And I will very quickly show how it can happen. The only thing that you need to do here is to create this pattern of the director. And the particles that differ in surface alignment would prefer different regions of this pattern. So here the particle with normal boundary conditions create a region on the right that is reminiscent of splay. And if you let this particle in the cell with these patterns, the particle of this dipole type would move into the splay regions, and the particle that prefers tangential orientation would move into the tangential stripes, into the stripes in which you have bend. The experimental evidence of that happening is very simple. You take the particle by the optical tweezers. It's just a laser beam that is focused that can trap the particle and move it around. And then you release it in some place where it doesn't want to be. Once you release, then this elastic background of the Lie crystal brings the particle to the location of splay, where it fits nicely because the splay around the sphere fits the splay of the background director. The next movie just shows that it's not just one particle. You can assemble many of them. All of them will go into these regions of splay and reside there. On the other, you can of course develop the theory of this. Viktor Pergamicek some time ago developed an approach how to describe colloidal interaction with a deformed director field, and we just use this potential of his to develop the equations for the dynamics, namely how the position of the particle along this pattern would depend on time. And fitting the experimental data with the theory, you would find that the energy of the elastic trap in the splay regions is extraordinarily high. It's thousands of Boltzmann temperature, so no thermal fluctuations at room temperature can kick these colloids away from the traps that are at the splay regions. So it's a very robust trapping, and once the particles are there, they are separated from these particles that go predominantly into the band regions just because of this band deformation. You see the results here. And that's it. After you separated the particles to splay and band, you apply electric field, and the electric field separates the charges, and then you might see that the splay regions move to the right, the band regions move to the left, and if you have the electric field applied and the particles are separated, then you will pull them to the left or right. You sort them out. You know that at the right end of your chamber, you are having particles with perpendicular anchoring or some type of molecules at their surface, and to the left would go particles that are of bolt type. And so this is the conclusion now about electrophoresis that is created by patterned surfaces at the Lie crystal boundaries. So unlike in the regular electrophoresis, we already seen these differences. There is some other things. By patterning the director, you create easily vortices. And vortices come naturally in the Lie crystal case because the V is proportional to E squared. In the isotropic electrolyte, what happens, since V is parallel to E, and as we know from Maxwell equations, curl of E must be 0, that means that curl of V must be 0. You cannot create vortices of flow by a uniform or electric field of any type in the case of linear electrophoresis. But in the case of Lie crystals, as you saw these little vortices in patterned director fields, it's a very easy thing to do. So finally, this is the latest development. Prior experiments were dealing with relatively weak electric fields, and that meant that the director is not perturbed by coupling to the electric field. It stays there the way you define it through surface anchoring, or the way you define it through the inclusions that are placed in the Lie crystal. But if you now apply much stronger fields, then what happens is that instead of the quadratic dependence, which is expected to be here, you have a much, much stronger response in the velocity versus E. You have something that can be satisfactorily described by higher order nonlinearities going beyond E squared. You have E to the power of 4 and E to the power of 6, which is a very steep dependence. And we think that it's related to the fact that at high electric fields, the director around the inclusion start to deform in response to the field, and that changes the local drag resistance, and it produces the much faster increase in the velocity as you see experimentally. But we have no adequate theory of that. So to make the conclusion of this part, we demonstrated that Lie crystals bring a new mechanism of separation of charges. It just happens because of director gradients. And as a result of that, the electrophoresis becomes a nonlinear phenomenon with quadratic dependence of the velocity on the field. And the main advantage is that now you can use an AC field to drive the steady flows. And I will either start or maybe finish with another example of electric field interaction with the Lie crystal. It relates to the subject of soliton. So this is the kind of restaged soliton that reminds the John Scott Russell's solitary wave observed in the shallow channel many years ago. So this wave propagates over huge distances without changing its shape. The amplitude remains the same. And it was Zabusky and Kruskal who studied much later on the collision of two waves of this type, and they realized that the collision results in reconstruction of the soliton. So they behave like particles, and because of that they introduced the word soliton. The Lie crystals as the medium in which solitons might exist is of course much richer than just water because of the director field. And in fact there were works by different groups in which people observed solitary waves of director realignment shown here in one-dimensional case. This is Peter Palfy and his colleagues created a kind of expanding ring of the director realignment. Lie crystals also allow some optical solitons to exist. This is Gaetano Santos' nematicons. It's the beam of light that is self-focused in the Lie crystal, and it's focused in the two orthogonal directions perpendicular to the propagation direction. And these nematicons have kind of interesting counterparts that are of extreme importance, so-called light bullets. Many research groups are now working on how to make the light being self-confined into small particle-like three-dimensional entities, like a bit of information, the so-called light bullet. So the difference between the nematicon and the light bullet is that this beam is kind of chopped into small parcels that do not spread. They just propagate along some direction, and they are of importance to create some optical telecommunication schemes. But in practice, they have not been achieved as stable formations. Turns out that each time you add a new dimension to the soliton, it's becoming harder and harder to stabilize such a soliton, because each dimension requires technically its own new mechanism of how nonlinearity and diffraction would compensate each other. So with this, I would like to just introduce you to the creations that are very similar to these light bullets, but they are formed by the director waves in a nematic Lie crystal. This is why we call them director bullets. No theory yet again. So just an experiment, which is a very simple experiment. You have a liquid crystal between two glass plates, and this liquid crystal has negative anisotropy of dielectric permittivity and conductivity anisotropy. So both things are negative. You apply electric field perpendicularly to the director, and these two conditions means that nothing should happen. The director should not realign, because delta epsilon negative means that this director prefers to be perpendicular to the field, which is already by design, and this is also means that flow of ions should not realign the molecules. And then you just prepare the cell, you apply the field, and see what happens. And what happens is very striking. You see a bunch of some formations, very bright distortions apparently of the director that go back and forth. You make this movie a little bit slower, and then you see how they interact. They bounce into each other, but they reconstruct themselves as nothing has happened. They just follow, and you can watch this movie for hours, and you would see this amazing thing. They are typically born not out of nothing. They are born at some irregularities. It can be some dust particles, as shown here. It can be also at the edge of the cell. This is the end of the electrode. This is the real time, the only movie that I show in the real time, just to show how fast these things are, much, much faster than the colloids that we demonstrated before. So this is just the same thing, but slower. You see how incoming solitons strike into the edge and kick out the new solitons out of here. And some of them just die at the edge of their universe. So this is an enlarged image of their collision. You see they kind of strike each other head to head, and then they separate, but the distance between them increases. So the next slide shows the kind of optical image of their profile before and after collision. So this is just the intensity of light measured by the microscope inside the body of this director bullet. So this is right before they met. This is when they meet and kind of mingle together. And this is when they separate. And you see that the director structure is practically the same before and after. This shows that they are interacting with each other. If the separation before collision is 0, which is this delta x, then after the collision, the separation is almost the half-width of the solid. And it means that if they meet like that, they repel each other and continue slightly shifted. If they already were separated like this, then and this separation was large, then they are not interacting, because the separation before and after is the same. But there is a small region of attraction. If they are slightly separated but not that far, they might actually come closer to each other. So they repel and attract each other. They show very different schemes of behavior. So I showed you how they reconstruct. Their meeting can result also in disasters like this. They just both disappear. The particle here can only be a motherboard for them, but can be also the gravestone. They just died there. And some of them come to the particle and get reflected backwards from the particle. So there is all sorts of interesting behavior. As a function of the electric field, you can control their concentration. If the electric field is relatively low, you have just few of them. And then as you increase the voltage, you have them growing in the numbers, which is just shown here how the phase diagram of the solitons depends on the electric field. So the most interesting thing is what is the director inside the solitons. And this is the reconstruction of the optical picture. So the director remains uniform away from the body of the soliton, and then inside it makes a little bulge like that. And then what happens is that with the electric field going up and down, we apply electric field, this bulge goes up and down. And since the bulge head and tail are different in the symmetry, this provides the directionality of motion. This slide just shows you that the tilts of the director are in sync with the field, electric field that is applied. This is just the next slide that shows you how this bulge goes up and down with half a period of the applied electric field. And there were many studies of electrokinetic instabilities in Lie crystals. Most of them saw these, domains rather than three-dimensionally self-confined particles. And the reason why it wasn't observed, we think, is related to the mechanism that we think is happening. So whenever you have the distortions of the director field, besides the typical dielectric and conductivity coupling to the applied field, you also have the so-called flexoelectricity. If you have the molecules with dipoles and you curve the director field, then the probability of the dipole to be oriented one way or the other would be different from 50-50. So if I have banana-like molecules with perpendicular dipoles, this is our molecules, then this bulge would create a polarization shown by the blue light. And the polarization is related to this expression of director deformations. Now you have electric field, and the electric field goes up and down, and it brings with itself the orientation of the polarization vector, and that creates the director motion, and it propels the soliton. If you take back on the envelope estimate of the force that is created by the coupling of this polarization to the electric field, you find some number which is matching nicely the viscous resistance to the motion of the solitons. So there is no theory yet, but it's a very interesting field that we are exploring right now, because it turns out that we can create solitons that not only move perpendicularly to the director, as in this case, we can also control the trajectories of this soliton. So it's a truly three-dimensional soliton with some propagation that you can control. And as I said, we have just understanding of what might be the mechanism, but there is no theory to explain, for example, how the velocity depends on the electric field. So I finish here, and tomorrow we will talk about two other things, living Lie crystals and a little bit about elastomers. Thank you very much for your attention.
Good, time for questions.
When you spoke about these light bullets, so you said that in practice they disintegrate, or they are not stable. I think you had it on your last slide. So why?
No, these bullets do not disintegrate. That's the point. They are stable. They move.
No, not the pneumatic ones, but in the introduction to this.
Oh, but that's you observe waves on I don't know, ocean, river. Those are not solitons. To have a soliton, you need to compensate for diffraction or dissipation with some non-linearity that would keep it together. So it's a self-confined situation. You always have two competing forces. One is dispersion, so that you create a bulge on the water surface. This bulge, by surface tension, would try to spread itself. You need to have some nonlinear mechanism that would bring it back together. For example, in the pneumaticons, normally you would have the light beam diffract, but since the electric field inside the light beam can realign the director, this realignment can focus through the anisotropy of refractive indices, the light beam back into the thing. And if the two completely compensate each other, then you would have a propagating beam that is straight and does not disperse.
Referring to the electrophoretic experiment, I was wondering if you can say something about the effect of ionic strength in microcrystals. So if you have a different concentration of ion, and second, what if you, instead of having 5 Hz, you change the frequency?
Yeah, if I change the frequency, then of course I would have something like that. So this is the velocity. If the frequency is very high, then the ions simply don't have time to separate, to locate themselves on the two opposite sides of the sphere. So this is why it's the case here. If the frequency is too low, then I'm kind of losing on efficiency of creating the flow. So this is the characteristic thing.
High could be what, 1 kilohertz or 100?
Yeah, no, it's unfortunately like 520 kilohertz. It's very low because you're mostly dealing with the response of the ions that have to move over relatively long distances, like 10 micrometers. So the frequencies here are very low. And regarding the question about the concentration and the nature of the ions, it's still work in purpose because it's, yeah, it's a very interesting.
Some of this ionic liquid crystal, I mean, which have organic
yeah.
absorbed.
Unfortunately, it looks like they have too much ions, and when we work with them, what happens is that the electric field causes electrohydrodynamics that is chaotic all over the place. There are too many ions, and they don't know how to behave nicely. So.
Any more questions? No.
Thank you very much.
Okay, Oleg, again.